This is SpaceTime Series 21, Episode 16. Coming up on SpaceTime. New studies show the Milky Way to be just as massive as Andromeda. The new measurement of the Hubble constant hinting at strange new physics beyond the standard model. And the most distant supernova ever seen. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims our nearest big neighbour, the Andromeda galaxy M31, and our own galaxy, the Milky Way, have about the same mass. The findings, reported in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org, contradicts earlier studies which concluded that Andromeda was 2 to 3 times larger than the Milky Way. The Milky Way and Andromeda are the two largest members of our local galactic group. The new estimate lowers Andromeda's mass to something like 800 billion times the mass of the Sun, which is on par with the estimated mass of the Milky Way. The Milky Way is a barred spiral galaxy with a diameter of between 100,000 and 180,000 light-years. It's estimated to contain between 100 billion and 400 billion stars. Located some 2.5 million light-years away is Andromeda, a spiral galaxy spanning about 220,000 light-years and containing an estimated 1 trillion stars. The most accurate previous estimate suggests that Andromeda's total mass was about 1.5 trillion solar masses, still almost double that of the Milky Way. If the new observations are correct, it suggests that Andromeda's dark matter halo must be far less massive than that of the Milky Way. One of the study's authors, Dr. Prajwal Kafli from the University of Western Australia, says the new research suggests that scientists had previously overestimated the amount of dark matter in Andromeda. The new figures were obtained using a new technique to measure the escape velocity required to leave a specific galaxy. You see, when a rocket is launched into space from, say, the surface of the Earth, it has to reach an escape velocity of 11.186 kilometres per second in order to overcome the pull of Earth's gravity from the planet's surface. Now, to escape the gravitational pull of the Milky Way, our rocket would need to reach an escape velocity of 550 kilometres per second. By examining the orbits of high-speed stars in M31, Kafli and colleagues were able to determine the escape velocity, and therefore the mass of Andromeda. With Andromeda no longer considered far more massive than the Milky Way, new simulations will be needed to calculate what happens when the two galaxies eventually collide in about 3.7 billion years' time. Kafli says the new numbers mean that suddenly 50 years of collective understanding has been turned on its head completely, transforming science's understanding of the local group. Astronomers previously thought there was one biggest galaxy, and our Milky Way was slightly smaller, but that scenario has now completely changed.
We're talking about a neighboring galaxy. Andromeda is our neighboring galaxy, right? So first thing is you take out your telescope, you observe stars. In this case, I observed what is known as high-velocity stars, so stars that are really moving with very high speed. And then you assume that those stars are very close to what is known as escape velocity. I looked at these stars, and then I worked out the escape velocity of the Andromeda galaxy, and then I backtraced it to how much weight there has to be in that galaxy for that star to come out from that potential with that much speed. So that was pretty much it in a simpler term.
When you measured these, you looked at the weight of M31, you looked at the mass of the Milky Way. When you looked at the mass of these two galaxies, most textbooks will tell you that Andromeda is a far more massive galaxy than the Milky Way. That's not what you found, is it?
Yes, exactly. I found quite opposite of that. And, you will find that step in the textbook and even in lots of literature. But this is not a solved problem. It's a pretty much an open problem because, there are other methods. So the one method that I discussed was what I use in my research. But there are other methods as well to calculate the mass of the distant galaxy. However, the problem with other methods had been that you also need a sidewise velocity of these stars. So in reality, what we only get for distant galaxy is a line of sight velocity. So you can only tell whether the star star is coming towards you or it's going away from you. You can't tell whether it's going leftward or rightward because you need to look at that star for hundreds of years to detect the motion, which is that tiny.
The proper motion.
Yes, that's what it's called, the proper motion. So it makes this method more robust. And when I use this method, which doesn't suffer from that problem that other literature work has been suffering earlier, I figured out that the mass is much less than what people have been claiming from last few decades. So here we go.
That's primarily, I guess, the baryonic matter you're looking at. You're also trying to include the amount of dark matter in that galaxy as well, aren't you?
Yes, you're right. So as your listener may already know that 90% of the galaxy mass is invisible, right? You can't see it, but it's there and you can feel it. So yeah, whenever you do the mass modeling of any galaxy, you can't simply count the number of stars and say that, maybe each star on average is equal to the weight of our own sun, and let's just multiply that number with the total number of star counts in any galaxy. It doesn't work that way because it's just roughly 10% of the total weight of the galaxy. So yes, you're right. So I have to also consider the weight of the dark matter, and then of course the visible component, which is galactic disk, and then buzz, and so on and so forth.
It was when you were looking at the dark matter component that you realized that the amount of dark matter in the Milky Way and the amount of dark matter in M31 is different.
Yes, because it is known just from the visual observation that the stellar mass, or the mass that we can see, or mass that remains in the form of stars in Andromeda, is slightly higher than what we know for our own galaxy. So that means that, and as my study suggests, overall mass of both the galaxy is pretty much equal, means that the amount of dark matter in Andromeda must be slightly smaller or less than what we got in our own galaxy.
That in itself is an interesting finding, isn't it? Because theories on cold dark matter right now do relate dark matter to the visible mass.
Yes, it's popularly known as what we call stellar mass-halo mass relation. Yes, our current best cosmological paradigm does make that kind of prediction about the relation about how the stellar mass should correlate with the dark matter mass. But it's pretty much theory, because even the simulation hasn't gone to what is known as the star formation history of the galaxies, and then all those gastrodynamics is still, we are not that advanced in our model, so that relation has quite a big uncertainty around it. And I have shown in my research that just comparing with that model, it seems that both our Milky Way and the M31 as well, both are quite off from the relation. So it either we are unique galaxies or we need to improve our theory.
That's Dr. Prajwal Kafli from the University of Western Australia and the International Centre for Radio Astronomy Research. You're listening to Space Time. I'm Stuart Gary. Okay, time now to take a break from the show and hear a word from our sponsor, Grammarly. If you write anything on the web, you'll become a big fan of Grammarly's. Their intelligent program will save you time and time again. Built by linguists and language lovers, Grammarly's writing app finds and corrects hundreds of complex writing errors, so you don't have to. You can easily copy and paste any English text into Grammarly's online text editor, or just install Grammarly's free browser extension for Chrome, Safari and Firefox. Grammarly's algorithms flag potential issues in the text and suggests context-specific corrections for grammar, spelling and vocabulary. Grammarly explains the reason behind each correction, so you can make an informed decision about whether and how to correct an issue. Grammarly helps you write mistake-free on Gmail, Facebook, Twitter, LinkedIn and nearly anywhere else you write on the web. And for SpaceTime listeners, Grammarly's offering a free download of the Grammarly software. To download Grammarly today, go to getgrammarly.com/spacetime. That's www.getgrammarly.com/spacetime so they know you came from us. And we'll include the link in the show notes as well. And now, it's back to our show. Astronomers have used NASA's Hubble Space Telescope to make the most precise measurements yet of the expansion rate of the universe since it was first calculated nearly a century ago. Intriguingly, the new results, reported in the Astrophysical Journal, are forcing astronomers to consider that they may be seeing something unexpected at work in the universe. That's because these latest Hubble findings confirms a nagging discrepancy which shows that the universe is expanding faster now than what was expected from its trajectory seen shortly after the Big Bang. Researchers suggest it means there may be new physics at work beyond the standard model to explain the inconsistency. The study's lead author, Adam Rees from Johns Hopkins University and the Space Telescope Science Institute, both in Baltimore, Maryland, says scientists are really grappling with trying to understand the meaning of this discrepancy. Rees and colleagues have been using the Hubble Space Telescope over the past 6 years to refine measurements to distant galaxies, using their stars as cosmic milepost markers. Those measurements are used to calculate how fast the universe is expanding with time, creating a value known as the Hubble constant. The team's new study extends the number of stars analysed to distances up to 10 times farther into space than previous Hubble results. But Rees's new value reinforces the disparity with the expected value derived from observations of the early universe's expansion 378,000 years after the Big Bang, the violent event which created the universe roughly 13.82 billion years ago. Those measurements were made by the European Space Agency's Planck satellite, which maps the cosmic microwave background radiation, the leftover heat from the Big Bang now cooled to just 2.7 degrees above absolute zero. The difference between the two values for the Hubble constant is significant, about 9%, and the new Hubble measurements help reduce the chances of the discrepancy in the values being a coincidence down to just 1 in 5,000. Planck's results for the Hubble constant place it at 67 kilometres per second per megaparsec, and even with the most generous reading it couldn't be any higher than 69 kilometres per second per megaparsec. This means that for every 3.3 million light-years further away a galaxy is from us, it's moving away at 67 kilometres per second faster. The problem is Rees's team have now measured the Hubble constant at 73 kilometres per second per megaparsec, indicating galaxies are moving away at a faster rate than implied by observations of the early universe. The Hubble data is so precise that astronomers cannot dismiss the gap between the two results as errors in any single measurement or method. Both results have been tested multiple ways, so barring a series of unrelated mistakes, this isn't a bug in the system but rather a real feature of the universe. Rees has outlined a few possible explanations for the mismatch, and all are related to the 95% of the universe that's shrouded in darkness. One possibility is that dark energy, already known to be accelerating the expansion of the universe, may be accelerating galaxies away from each other with even greater or growing strength. This means that the acceleration itself might not have a constant value in the universe, but changes over time. Another idea is that the universe may contain lots of new subatomic particles that we don't know about, but which are travelling at close to the speed of light. These particles are collectively referred to as dark radiation, and they include previously known particles like neutrinos, which are created in nuclear reactions and through radioactive decay. Neutrinos oscillate between three specific types or flavours: the electron neutrino, the muon neutrino, and the tau neutrino. These interact with the rest of matter only through gravity and the weak nuclear force. In fact, these are so small that for a while they were thought to be massless. Scientists think the three types of neutrinos we know about may not be the end of the story, and there's a hunt going on right now for a new hypothetical particle known as a sterile neutrino, which would only be affected by gravity. Yet another possibility is that dark matter, that invisible substance which only interacts gravitationally with normal matter, might be interacting with normal matter and/or radiation more strongly than previously thought. Now, any of these scenarios could change the contents of the early universe, leading to inconsistencies in theoretical models. And these inconsistencies would result in an incorrect value for the Hubble constant, inferred from those observations of the early cosmos. It would explain why these values are at odds with the numbers being derived from the Hubble observations. Before the Hubble was launched by the Space Shuttle in 1990, estimates for the Hubble constant varied by a factor of 2. One of Hubble's key goals was to help astronomers reduce the value of this uncertainty to within an error rate of only 10%. Astronomers have been steadily refining the Hubble constant by streamlining and strengthening the so-called cosmic distance ladder, which, as the name suggests, astronomers use to measure cosmic distances. Scientists have compared those distances with the expansion of space-time itself as measured by the stretching of light from receding galaxies, the so-called redshift. They've then used the apparent outward velocity of galaxies at each distance to calculate the Hubble constant. Of course, the Hubble constant's value can only be as precise as the accuracy of the measurements. Traditional cosmic distance ladders involve using the parallax method to measure short distances. You see, by first looking at an object, say a star, from one side of Earth's orbit around the Sun, and then looking at the same object from the opposite side of Earth's orbit around the Sun 6 months later, and then comparing both views of the star with background stars that don't appear to move, scientists can calculate the distance to nearby stars using plain old trigonometry. As we mentioned last week, you get exactly the same effect by holding out your thumb in front of your nose at arm's length, and then looking at it by alternatively closing one eye and then the other. To measure distances to more distant objects, astronomers use standard candles, such as stars known as Cepheid variables. Cepheid variables are stars which brighten and fade at set rates based on their mass. So, by knowing the mass of a Cepheid variable through its pulsations as it brightens and fades, astronomers can then determine how intrinsically bright the star really is, and compare that to how bright it appears. Then, by using the inverse square law, astronomers can determine the distance to that star. The inverse square law shows that a specific physical quantity or intensity is inversely proportional to the square of the distance between the observer and the source of that physical quantity. It's the same sort of effect you get when looking at a row of streetlights down a dark road. The further away each of the streetlights are, the dimmer they'll look, even though all the streetlights actually have the same luminosity. To measure cosmic distances to more distant objects, astronomers look for a type of exploding star known as a Type 1a or thermonuclear supernova. Because these stars all explode with roughly the same mass, and consequently with roughly the same brightness or luminosity, it again allows astronomers to use the inverse square law to determine distances. The latest Hubble results are based on very accurate measurements of the parallax of 8 newly analysed Cepheid variable stars within the Milky Way galaxy. These stars are between 6,000 and 12,000 light years away. That's around 10 times further than any previously studied. To measure parallax with Hubble, recent colleagues had to gauge the apparent tiny wobble in the Cepheids due to Earth's motion around the Sun. Now, these wobbles are the size of just 1/100th of a single pixel on the telescope's camera. Or to put that another way, roughly the apparent size of a grain of sand seen 160 kilometres away. Therefore, to ensure the accuracy of the measurements, astronomers developed a clever new method that wasn't envisaged when Hubble was first launched. The authors invented a scanning technique in which the telescope measured the star's position 1,000 times a minute every 6 months for 4 years. The authors calibrated the true brightness of the 8 slowly pulsating stars and then cross-correlated them with the more distant pulsating cousins in order to tighten inaccuracies in their distance ladder. The researchers then compared the brightness of the Cepheid variables with thermonuclear supernovae in those same galaxies with a better degree of confidence. This allowed them to more accurately measure the star's true brightness and therefore calculate distances to hundreds of supernovae in far-flung galaxies with far more precision. Another advantage of this study is that the team could use the same instrument, Hubble's Wide-Field Camera 3, to calculate the luminosities of both the nearby Cepheids and those in other galaxies, thereby eliminating systemic errors that almost unavoidably turn up when comparing measurements from different telescopes. Now, ordinarily, if every 6 months you try to measure the change in position of one star relative to another at these distances, you're limited by your ability to figure out exactly where the star is. But this new technique sees Hubble slowly panning across a stellar tangent and capturing the image as a streak of light. The method allows repeated opportunities to measure the extremely tiny displacements due to parallax. The team's goal is to further reduce the uncertainties by using data from Hubble together with the European Space Agency's Gaia Space Observatory, which will measure the positions and distances of stars with unprecedented precision, hopefully explaining the ongoing discrepancy in the Hubble constant. I'm Stuart Gary. You're listening to SpaceTime. Astronomers have confirmed the discovery of the most distant supernova ever detected. The findings, reported in the Astrophysical Journal, claim the huge cosmic explosion took place some 10.5 billion years ago, meaning it's taken some 3/4 of the age of the universe for light from this blast to reach Earth. The exploding star, designated DES16C2NM, was detected by the Dark Energy Survey, an international collaboration of over 400 scientists from more than 25 institutions. The survey aims to map 300 million galaxies in order to find out more about dark energy, that mysterious force believed to be causing the accelerated expansion of the universe. DES 16C2NM is classified as a superluminous supernova, the brightest and rarest class of supernovae. A supernova is the explosive destruction of a massive star at the end of its life. Superluminous supernovae were first discovered 10 years ago. They're thought to be caused by a material falling back onto the rapidly rotating neutron star, which was originally formed through the core collapse of the progenitor star when it went supernova. The study's lead author, Dr. Matthew Smith from the University of Southampton, says as well as being extremely distant, extremely bright and extremely rare, the discovery provides astronomers with unique insights into the nature of superluminous supernovae. You see, the ultraviolet light coming from this event tells scientists about the metals produced in this explosion, as well as the temperature of the explosion itself, both of which are key to understanding what causes and drives these cosmic events. DES 16C2NM was first detected back in August 2016, with its distance and extreme brightness confirmed in October of that year using three of the world's most powerful telescopes, the Magellan and Very Large Telescopes in Chile and the Keck Observatory in Hawaii. You're listening to Space Time. I'm Stuart Gary. And time now for a brief look at some of the other stories making news in science this week with a science report. There's a grim new warning out today that the climate change problem is now so bad that sea levels will continue to rise, even if all the recommendations and targets of the Paris Agreement on global warming were followed. A report in the journal Nature Communications has found that new climate models estimate that global sea levels will rise by between 0.7 and 1.2 metres by the year 2300, assuming the Paris targets are fully met. But for every 5-year delay in mitigation efforts, scientists say another 20 centimetres of sea level rise will be added. Well, most parents think of their kids as innocent children. A new study has found that at least 15% of teens are sending sexting images to their friends, and almost 30% of teens admit receiving them. The findings, reported in the Journal of the American Medical Association Pediatrics, are based on a Canadian review of 39 studies. The review included some 110,000 teens aged between 12 and 17 and covered the years 1990 through to 2016. Scientists have found that numbers have been increasing in recent years, with older teens sexting far more than their younger peers. Researchers were especially concerned about 5 studies which examined the non-consensual sending of sexting images, with about 10% of kids reporting either forwarding an image without consent or having one sent to them without their prior consent. Scientists have produced the first 3-dimensional computer models of the now extinct thylacine or Tasmanian tiger. The new simulations reveal how the Tasmanian tiger develops from a joey to adulthood. Researchers from Museums Victoria and the University of Melbourne carried out detailed CT scans of all 13 known Tasmanian tiger joey specimens. They created a 3-dimensional digital model which allowed them to study the skeletons and internal organs of these marsupials and reconstruct their growth and development. The digital scans show that when first born, the thylacine pup looks just like any other marsupial. But by the time they're 3 months old and venturing out from mum's pouch, they look more like a puppy and continue to grow with a dog-like appearance. In fact, the marsupial's resemblance to the dingo is one of the best-known examples of convergent evolution in marsupials. This is where 2 separate species, despite not being closely related, end up evolving to look very similar. The Tasmanian tiger would have last shared a common ancestor with the canids, that's dogs and wolves, something like 160 million years ago. Once ranging throughout Australia and New Guinea, the Tasmanian tiger disappeared from the mainland around 3,000 years ago, most likely due to competition from humans and dingoes. Sadly, the remaining thylacine population, isolated on Tasmania, was hunted to extinction in the early 20th century by farmers and politicians, with the last known individual dying alone in the Hobart Zoo in 1936. A new study warns that hackers really could take control of a patient's implanted electronic cardiac devices such as pacemakers. The findings, reported in the Journal of the American College of Cardiology, explores the risks and outlines how cybersecurity could be improved. There haven't been any recorded cases of cardiac devices being hacked so far, but medical devices have been targets of hacking for over a decade, and targeting cardiac devices has been shown to be possible. The problem is many of these devices now communicate wirelessly with healthcare providers, and that could provide hackers with a way in. However, the authors conclude that hacking is not currently a relevant clinical problem, and the benefits of wireless communications with devices far outweigh the risks, at least for the moment. Rumours are abuzz that the next generation of iPhone and iPad won't feature the traditional home button. Of course, when it comes to Apple, there's always been a strong rumour mill. To try and sift through the latest fact from fiction, we're joined by Alex Zaharov-Reutt from IT Wire.
Well, there's a bunch of different things that have popped up over the past week. One is that the future iPhones coming later this year will all feature the same kind of design as the iPhone 10. They'll have the notch at the top, and they won't have any home buttons because they, it's all about gestures and swiping upwards and not having to have fingerprint readers on the front of the phone and having the screen go right to the edges, which is the thing that everyone's now trying to do.
Almost right to the edges. We still have that notch. I don't like the notch.
I'm talking to you on an iPhone 10 right now, and I see the notch every day. It's there, but it's a lot of people are saying it sort of becomes invisible, and I mean it doesn't. It's there, but it would be better if it wasn't there. But for me anyway, it's not a deal breaker, and it's been their most popular phone ever since sales of the iPhone 10 started. So it certainly has been very popular, and the notch doesn't seem to have dissuaded too many people from buying it.
Have they solved the problem with the batteries now? We know Samsung had a huge battery problem. Batteries were overheating and catching alight, and there were reports after the 10 came out that the same thing was happening to Apple.
Look, there were one or two isolated cases of problems with iPhones. I mean, there has been over the past 2 or 3 years, but these cases are very few and far between, unlike with the Samsung Galaxy Note 7, where there was sort of an ongoing
major recall.
Exploding phones. Yeah, 2 major recalls. Look, everyone would have been very much on edge, as it were, and checking battery chemistries. Apple has always been very strong on battery chemistry. They always wanted to make them thinner, and so they've tried to squeeze more out of the battery. Now, Apple did have the problem where, because it's been pushing its batteries so much...
Well, they had to slow down the program, didn't they?
They had to slow down their phones.
And they didn't bother telling us they were doing that, which is very naughty of them.
It was. I mean, they did say it, but they didn't sort of broadcast it from the rooftops.
What are the features we can expect this year?
Well, more edge-to-edge displays. It's still always the standard stuff. Better cameras, hopefully longer battery life. But what surprises are in store? There hasn't been too many rumours out there yet. It's always interesting to know what rumours actually come true. But at this stage, I don't know what surprises are in store. But clearly, everything will be incrementally updated. That's always the way. But we are also expecting to see next year larger phones. So, there's talk of a 6.5-inch iPhone 10 Plus version, and also a 6.1-inch version with an LCD screen, which won't have the more expensive OLED screen and might not have wireless charging. It might have, but we're yet to all find out. But there is talk that the 3 phones coming this year will all have the same edge-to-edge screen, and that's going to be the beginning of the edge-to-edge displays for everything, and that should also come to the iPads as well.
Are Apple up there with the rest in terms of the features they offer?
Yeah, generally speaking, I mean, look, you have had people like Samsung and others offering wireless charging for years. Apple only introduced that last year as an example. You do have things like higher megapixel cameras that other companies have offered. I mean, Samsung even went to the extent of offering in the Samsung Galaxy S4 the ability to use your head or your eyes to move pages up and down without having to touch the screen. But sadly, they didn't actually do that for the Samsung S5. They sort of started deprecating that feature.
That's Alex Zaharov-Reutt from IT Wire. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary. At Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.